this we have, this is known as projection function on x1 cross x2 to x1, which is defined as P1 of, and element here is order pair x1 x2, which is equal to the first component x1. Similarly P2, so in general we call it Pi, from x1 cross x2 to xi, I is 1 or 2, then Pi of order pair x1 x2 is xi. Then our aim then was to define a topology tau on x1 cross x2 having the property that such that this Pi projection functions from x1 cross x2 to xi is continuous with respect to the topology we are going to define on x1 cross x2, that is known as product topology. That is, the topology tau on x1 cross x2 is the smallest such topology which makes each Pi continuous. Then this we have seen, this can be extended to any finite, now finite product with the same motivation that then it will be a function from, we have x1 x2 xn topological spaces with tau x1 with topology tau 1, tau n topology on x, then Pi the ith projection function from x1 cross x2 xi cross xn to the ith coordinate, that is defined as Pi of x1 x2 xi xn is the ith component. Then we give a topology on the Cartesian product x1 cross x2 etc. cross xn. So if we call this is our x, then this Pi from capital X with respect to that topology known as product topology to ith component xi tau I is continuous, each Pi is continuous, and we do not want just any topology on x which has that property, we want a among all the smallest topology which has this property, that topology we call it product topology on x1 cross x2 xn. So in fact we have seen, keeping that in our motivation, then we have proved that, I mean we define in a natural way the topology, then we have seen that set of all u1 cross u2 cross un such that ui belongs to tau I varies from 1 to n, is this will be a subcollection of the product topology, in fact, and this is a basis for the product topology, or we will have a subcollection and this subcollection is a basis for a topology on x1 cross x2 xn. The topology generated by discrete beta is our, this is the product topology. We can define in different ways. So now with the same motivation, let us see how to define the product topology on arbitrary collection. So, we have an index set J. Let us assume that index set is J on arbitrary non-empty index set, and for each alpha belongs to alpha belongs to J, we have a set X alpha. So, then we want to define a new set, that is our Cartesian product pi x alpha, alpha belongs to J. So, what do you mean by first this Cartesian product, which we call it X. So, now let us see what will happen when we have n sets, say x1, x2, xn, we have n sets, then we have defined, we have in fact assumed that we know the Cartesian product X equal to x1 cross x2 cross xn. Now, we will identify each element here, we identify x belongs to capital X if and only if x equal to x1 comma x2 comma xn, an n tuple. Now, that is you give for the first component 1, with that we associate an element x1, with 2 we associate an element x2, and so on with n xn. So, we have a function f from where our index set, here in this case index set is 1 to n, this is our J. 2 where the image of 1 is x1, that is in capital X1, image of 2 is x2, that is in capital X2, image of n is xn, that is in capital Xn. So, it can be image it may be in x1, x2 or xn. So, we have a function from our index set to xi, I 1 to n. It is not just any arbitrary function, having the property that f at each xi, f at I. So, say that the I component f at I equal to, that is only a notation, what we want is it belongs to our xi, and this fi we call it xi, that is just a notation. So, that is what is the Cartesian product x1 cross x2 cross xn means this is set of all function from our index set 1, 2 to n, this is our domain, to union xi, I varies from 1 to n such that f at I belongs to the ith coordinate space xi. So, we identify each element of this Cartesian product as a function. So, with the same, now it will be easier for us to define what we mean by an element in the arbitrary Cartesian product, that is now. So, keeping this in mind, define phi x alpha, alpha belongs to J. J need not be a finite set, it may be countable or even uncountable. So, which is defined as set of all function f from the index set j to union x alpha, alpha belongs to the index set j, such that f at alpha belongs to, such that for each alpha, f alpha should belongs to capital X suffix alpha. This normally we denote f alpha by x suffix alpha. So, like a sequence, our index set may be set of natural number, then f from n to union say xn, n 1 to infinity. See, so xn may be equal to the same set x. So, then fn is an element xn, that xn belongs to capital Xn. If all the xn's are equal to same set x, we say that it is a sequence in X. So, for us here each element in the Cartesian product is a function having this special property. So, the next question is, what will happen? Suppose we have for each alpha belongs to j, x alpha is non-empty. So, what can we say? What can we say about the Cartesian product, that is this x? Say about x, that is, can we say that this set is non-empty? So, when each x alpha is non-empty, then the Cartesian product is also non-empty. In fact, this comes from the axiom which we call it axiom of choice. So, we will just recall what is an axiom of choice. Axiom of choice, that is, we have a collection exactly like this, x alpha, alpha belongs to j, a collection of non-empty sets, that is, it is like we have a collection x alpha, a collection of non-empty set, then we can form a new set say C, which contain exactly one element from each set x alpha. I mean that existence of such a set we call it the axiom of choice. That is, in other words, exactly the same thing. We have a choice function defined as f from j to this union such that f alpha belongs to x alpha. Such a function exists that comes from the axiom of choice. This is known as choice function. I mean, this will assume that from axiom of choice, this set is each x alpha is non-empty, imply for each alpha x alpha is non-empty, then this will imply our Cartesian product also non-empty. That is, essentially this is axiom of choice. Axiom of choice is equivalent to this property, that is, each x alpha is non-empty mean the product is also non-empty. That means we have at least one function from j to union having the property that f alpha belongs to x alpha. So, now we have defined the Cartesian product. Now, again our aim is to introduce a topology which is not very large but at the same time it has the property that so each projection function. Now say let us fix say alpha naught, or we call it say fix beta belongs to the index set j. Then for each such beta define p suffix beta from our Cartesian product phi x alpha, alpha belongs to j, to this coordinate space that we call it, that is x suffix beta. This beta is fixed, like the finite number of sets x1 cross x2 xn, we have p1 from x1 cross x2 to x1, or pi from x1 cross x2 cross xn to xi. So in the same way we define this as p suffix beta. What is an element here is a function f, and what is how we define f? If we take an alpha in j, that f alpha will be in x alpha. So we have fixed the beta from j, then the image f beta that will be in x beta, that is what our we call, that is our image. This we can call, normally we denote by x suffix beta. So that case our f is, we call it f means set of all f alpha, alpha belongs to j, which we call it x alpha, alpha belongs to j, where f alpha equal to x suffix alpha for all alpha. Okay. So hereafterwards will simultaneously sometime we will use f, or also we use f equal to this x alpha, alpha belongs to j. So now we have defined like this finite product. So that is what our projection function. From if we take an order pair x1 x2, you product either on the first p1 of order pair x1 x2 is x1 first projection, or on the y axis second p2. So like that for each beta we have a projection function, or also we call it coordinate functions. Now our aim is to introduce or to define a topology on our Cartesian product. Say that topology, that is we are going to call the product topology, say tau. With respect to that topology, that each p alpha p suffix beta should be continuous. That is our aim is to define a topology say tau on x, which is equal to, I mean our notation is pi x alpha, alpha belongs to j, such that, I mean satisfying the following properties, namely first for each beta belongs to j, this projection function from the product pi x, or we call it say pi x alpha, alpha belongs to j, alpha where is beta is fixed. Here with the proposed topology tau to x beta, tau beta, this should be continuous. And second, This is the smallest such topology having this property, meaning is whenever, like last class we have seen exactly same, whenever tau prime is a topology, so topology on pi x alpha and the Cartesian product pi x alpha, alpha belongs to J, having the property that is such that each p suffix beta, that means beta belongs to J, so that pi x alpha, alpha belongs to J. Now our topology is this tau prime 2 x beta tau beta, this is continuous, so that each projection function is continuous with respect to tau prime on this Cartesian product, continuous. So we have another topology on this Cartesian product which makes each projection function continuous, then our topology is the smallest such topology, then this happens mean our tau should be a subcollection of tau prime. So this is our motivation. So keeping this mind, what is the first, we want that this is continuous, that means inverse image of open set is open. So fix beta, then we call it say script s suffix beta. Why we define this is take an arbitrary open set in x suffix beta, then what is the pre image, we call it p suffix beta inverse of say u suffix beta, where the u suffix beta is an arbitrary open set in our x beta, that means this belongs to tau beta. So u beta belongs to tau beta, and we want that all this p suffix beta inverse of u beta should be in our product topology, that means our product topology should contain this collection script s suffix beta. So this varies, if we vary this fix beta, define s beta like this, and script s, we want that each p suffix beta is continuous. So we take union of script s beta, beta belongs to J. Now here beta varies, I mean this is same as we want union of script s alpha, alpha belongs to J, I mean it is just a notation variable. Then now what is our requirement is our product topology is such that it contains this collection script s, and now it is easy to see that this subcollection script s is a subbasis for a topology on the Cartesian product. So what is, we have seen already how to define a subbasis, just recall. So a subcollection, so we have given x a just a set, script s subcollection of power set of x, then script s is called subbasis for a topology on capital X if and only if union of a from script s equal to the whole space. So if this condition is satisfied, then from script s, I mean if you take all the possible finite intersections of members of script S, that we call it script beta. That script beta will form a basis for a topology on this set X. Then that topology generated by script beta is what the topology we need. What is that topology is such that it is the smallest topology which contains script S. So, that is what important. We want that a topology on capital X which contains script S, and it is the smallest such topology. That means naturally we consider the collection of all topologies, then the intersection of all such topologies is our required topology. So keeping this in mind, so now we prove that this is a subbasis. In fact, if we fix any element for each beta belongs to J, in fact what is P suffix beta inverse of U beta, where for each beta belongs to J, U beta belongs to tau beta, that is U beta is open in X beta. This is by definition those F in our domain is the Cartesian product pi x alpha alpha belongs to J, such that image of this under this function. So, we know that P beta inverse is set of all F such that P suffix beta of F should belongs to U beta. But what is this? This is same as set of all F belongs to pi x alpha, alpha belongs to J, such that by definition P suffix beta of F is F at beta, F at beta, this is what we call it x suffix beta belongs to U beta, and there is no restriction for F alpha when alpha not equal to beta. So, we can prove that this is same as pi of, just we will write A alpha, alpha belongs to J, can easily verify that this is same as pi A alpha, where A suffix beta, that image should be in U beta, that will coincide with U beta, and A alpha equal to the whole space x alpha when alpha not equal to beta. See, in fact this itself in particular our U beta, if U beta equal to x beta, then P alpha inverse of x beta equal to the whole space x. So, this script S is union of such members P alpha inverse of, that is P beta inverse of U beta. So, in other words we can define script S is same as set of all P alpha inverse of U alpha, such that U alpha belongs to J, U alpha belongs to tau alpha, alpha also varies, that is same as this union. So, this will give us this script S union of, that is union of A belongs to script S is obviously this is the whole space. So, hence this will form a sub-basis for a topology on the Cartesian product. So, now how the next is script, this imply script S is a sub-basis for a topology on the Cartesian product on pi x alpha, alpha belongs to J. So, now what is our, from sub-basis we will have to go to, from script S go to basis, sub-basis to basis, then basis to topology, topology on our Cartesian product. Okay. This we call it tau, that is our topology. So, what is scred beta, and A belongs to scred beta if and only if A can be written as finite intersections of, we will assume that non-empty intersection, mean the index set is non-empty. So, A will be equal to say some B alpha 1 inverse of U alpha 1. So, that is we are trying to write A as a intersection of P alpha 1 inverse of U alpha 1, P alpha 2 inverse of U alpha 2 intersection say P some alpha n inverse of U alpha n. That is we are writing A, here our index set is alpha 1 alpha 2 alpha n. This is a finite subset of our index set J. I mean, let us assume that this is non-empty, this index set subset is a non-empty subset of J, then A will be an arbitrary members will be like this when then in this case. So, we have seen that what is this, this contains pi some A alpha, alpha belongs to J, where A alpha 1 will be equal to U alpha 1, all other U alpha will be the whole space. Similarly, here this will be alpha 2, corresponding to alpha 2 it is U alpha 2, the remaining place the whole space. So, you can easily see that this will give us A will be equal to, that is this will imply. So, this we have seen last class, similar to that A will be equal to pi of A alpha, alpha belongs to J, where A alpha equal to exactly this U alpha 1, A alpha, I mean we can say that just A alpha equal to U alpha belongs to the corresponding tau alpha when alpha equal to alpha 1 alpha 2 alpha n, and otherwise it will be the whole space, and A alpha equal to the whole x alpha when alpha not equal to alpha 1 alpha 2 alpha n. So, this will give us an arbitrary members of the Cartesian, I mean our product space. So, in the from the basic, this is this is going to be our basic open set. So, in particular each A alpha may be the whole space. So, that is here what is main thing is only the finitely many components of this A alpha will be a proper open sets in the corresponding x alpha, the remaining thing the whole space. In fact, yeah, this will give us, later we will see that, see for example when x equal to r, x1 is r, x2 is r, I mean there is no restriction on x1 x2, all can be the same set. Then go to our the Cartesian product r cross r, that is our plane R2, R2 r cross r. So in fact if we take a open interval which is our basic open set in R2, sorry basic open set in R. So here another basic open set again in R, but here this we call that y axis. Then the natural, this is what our natural basic open set in the Cartesian product, our product topology. So that is the open rectangle. So we have this open rectangle except the boundary. This the open rectangle is a basic open set, is a, I mean this open rectangle is a basic open set in R cross R. In fact we can prove that more generally, if beta 1, if we have a beta 1 basis for x tau 1, basis for we can just say tau 1 for the topological space x1 tau 1, beta 2 basis for tau 2, then this together implies, this implies split beta equal to set of all a1 cross a2 such that a1 belongs to beta 1, a2 belongs to split beta 2, yeah this is a basis, this is a basis for basis for x1 cross, I mean basis for our, okay we will write x1 cross x2 tau, tau is our product topology on x1 cross x2. So that means here exactly this is like our usual open rectangles, they will, that such collection will form a basis for R cross R, that is our plane R2. So here our basic open sets are all of this type. Now once we, in fact as we have pointed out, for all practical purpose it is enough if we know the collection of all open sets, that is the collection of all basic open sets in our topological space. Then using that we define only, that means if we know a point is an interior point or a point is in the closure or limit point or continuity, all the concepts later we will see. In fact one of the motivation to define the product topology is this way is, we are going to have prove what is called Tikhonov's theorem, yeah a non-trivial theorem which says that, I mean we will later define, if each x alpha tau alpha is compact, meaning is if you have a collection of open sets of some topological space A x, script A we have the topological space x tau, script A collection of open sets in x. So that means script A is subcollection of tau and this covers the whole space, x equal to union of A belongs to this collection. We say that such case script A is an open cover for x. See this may be a large collection of open set script A, compact means In such a case we do not require such a large collection, that should imply from that we can extract some finite member from script A such that that is sufficient to cover our X. So, this what we say that script A is an open cover for X, then it has a finite subcover, then such a topological space is called compact. So, if each X alpha tau alpha is compact, this is compact, this will write for compact, this implies the Cartesian product will be also compact, that is what Tikhonov's theorem. So, if we see that, that is exactly the motivation. So, if we have a open interval, if we have a closed interval, here closed and bounded interval, that is the ideal compact sets. I mean any in R any closed and bounded set later will prove that they are all compact. Every closed and bounded set is compact. Bounded suitably will define, I mean A will be contained in a closed interval. So, this will be a rectangle. So, if it is R3 will have a cube, but this case if we extend it, if we allow our collection, that is what we later we are right now we are going to define what is called box topology. Now, this contains larger collection of open sets, so like discrete, then the chances of having this property will be less. I mean our aim is to see that this collection contains a smaller collection, but at the same time it will have some nice open set. From that we can any collection of open sets which covers capital X, we can extract a finite subcollection. In fact, one of the main motivation is to define the product topology this way is to prove the Tikhonov's theorem. So, now let us quickly define what is called the box topology. See for us, so hence what is the product topology? In short, product topology is, we call it product topology tau, but we know only how the basic open sets are is such that set of all phi u alpha, or it does not matter which you write, phi u alpha or a alpha, alpha belongs to J, such that we can call it each a alpha belongs to tau alpha, for all alpha belongs to J, and a alpha equal to the whole space X alpha except the for finitely many alpha 1 alpha 2 some alpha n. We are not telling n is fixed for any finite except finitely many a alphas, remaining a alpha should be the whole space for alpha 1 alpha 2 belongs to J. This what our, then what is product topology mean? This topology generated by script beta equal to our product topology. This has the property that how we got this topology is keeping in our mind each projection function from pi x alpha to x beta continuous, and this is the smallest topology on our Cartesian product having this property. So, other natural way is if we define, now we have the same collection x alpha, tau alpha, alpha belongs to J, an arbitrary collection of topological spaces. Now we consider the boxes. This is similar to, I mean exactly it looks like a box, phi of u alpha or a alpha, say we call it pi u alpha, alpha belongs to J. So, each u alpha comes from the corresponding tau alpha, no restriction, set of all u alpha such that set of all pi u alpha such that each u alpha belongs to tau alpha. If we call it this collection as screed suffix beta, this also a basis for a topology on our Cartesian product pi x alpha, alpha belongs to J. So, hence by definition the collection screed beta, we call it from here, this collection screed beta is a subcollection of screed beta suffix b. Hence the product topology tau induced by screed beta is a subcollection of tau suffix screed beta suffix b. Let us call this is tau suffix b, that is box topology. I mean the topology induced by or generated by screed beta suffix b is called the box topology, which is stronger than tau. So, now let us quickly see that how these two topologies are different. See, if we take now consider xn, our index set j equal to set of natural numbers j, and for each n xn equal to r. That this is standard notation, we call it r power omega equal to r cross r cross r. I mean this is what, this is same as telling that pi of xn n1 to infinity, where each xn is r. So, now we can have, see this is one topology, we have this tau, we call it product topology on r power omega Cartesian product, tau suffix beta box topology on r power omega. Now we will define a function, define f from the set R will define from the set R to r power omega as f of t, t is an element in R, then f of t is t again an element in R, comma t that, because we want this should belongs to R cross R cross R cross etc. That is, then f is a function from R to r omega. Now give what will happen to R here with usual topology and the domain. Here you consider one way box topology and another R power omega with box topology, and then in the next lecture let us discuss what will happen to the continuity of this function with respect to these two topologies. Okay. Thank you.